Hello everyone and welcome into yet another live stream, and today we will try to answer the question of how the heck do transistors work in reality, actually, for real. And hi the gorgeous, welcome to the live stream. I should probably ping it on Discord. Let me just... And also music, oh yeah, I always forget. I always forget about the music. So... And there it is. Everything should be working as well now. So, as I mentioned, they'll try to answer the question how the heck transistors actually work, because I know the basic idea behind them, but they are so much more complex that I'll need an entire live stream to understand. And I feel like the solid place to start would be engineering, I suppose, tab of LibraText. Feels like a pretty solid way. How can we help you? Transistors. Speeds, I don't know yet. PNP transistor, yes, precisely. That's precisely what we need. Transistor technology, this is chapter 1.3, which is a very early chapter. MOSFET will probably be also important. Transistor equations. Oh, this is extremely important, that's great. And for now, let's leave it there. Maybe one more transistor equations page. Cool. So, transistors. Oh, this is gonna be fun. Aren't I glad I promised this last year? Oh, the great and swell idea at the time. So... I'm not doing this sober, no way. Okay. Transistors are semiconductors devices with 3 and sometimes more terminals. The third terminal name was the output current to be controlled by a relatively small no power input signal. The third terminal. That's already news. That's great. In amplifiers, transistors are used to achieve the current gain, voltage gain, or power gain. Most of the... amplifier, it's in the name, makes sense. Most of the power gain is the objective or in RF microwave design. Most transistors are fabricated using silicon, don't really care about fabrication. Silicon technology, yeah, germanium. Fundamental type okay. 3 fundamental types of microwave transistors. What about others? Oh. The first of all, being the most common kind. Okay, I know MOSFET, so hi Sweezo, welcome. I'm trying to figure out how transistors work. Okay. 3 fundamental type transistor shown figure on, yeah. Alright, so we have BJT, MOSFET, and JFET. I'm already kind of familiar with MOSFET. This graph is so dense and tiny. There's a lot of things going on. Great. Okay. Because hi there, Isaac, welcome. A bipolar transistor has 3 semiconductors regions called the collector, base, and emitter. Okay. NPN BJT has N-type semiconductor, the emitter and collector, and P-type semiconductor forms the base. It's an NPA BJT N-type semiconductor. I mean, no wait, it's an NPN BJT. It's simple. Okay. Positive sense of current flow is from the collector through the base emitter. And the dominant... This is not a great start. I guess that's probably because it's from microwave and RF design, so that's probably why. This one's from FETs, so... Oh, the very first one's Introduction to MOSFET. Actually, this looks to be Albotron. That's seems like a much better one. I'll make it. Hi there, hi Laplace, welcome, Lashim. Return device transistors. The transistor, okay. In truth, this device has at least 4 or probably 5 terminals, but we will leave the subtle details for later time. You know those subtle details like 2 extra terminals. Oh, those little subtle, those irrelevant things. We don't really care about those. We will now focus on a device called field effect transistor or metal oxide semiconductor field effect transistor MOSFET. Or simply the MOSFET, precisely. The vast majority of transistors in use are MOSFETs. If you are reading this on device, you are probably writing several bit MOSFETs. Sick. So. Oh, I guess an N and P semiconductors. I guess I should also probably get them first. Oh yeah, this is what. Oh, with bonding. That's where we start. With bonding. Well, quite a backstory, isn't it? It's one of those live streams where, like, in order to understand something which seems simple, you need 70 different lessons. Because, of course, properties of metals, yeah. I think that people this. Yeah. Okay, we don't really care about those yet. Or maybe. Okay, this is useful actually to remember for later. But not for this live stream. There we go. OBS Studio just really quickly had to disconnect. Now this. Hawaiian metals, good conductors. Yeah, okay, this is basics. Or maybe up to the band structure of metals. Maybe not, this is going really in depth. I guess it is material science for electrical engineering, so I guess it makes sense. Obsolete provides a clear set of criteria for the distinction between conductors, insulators, and semiconductors. As we have seen, the conductor must possess an upper range. Now, levels not only partially filled, valent electronic levels can be think yeah. Insulators is characterized by a large gap between the highest fill band and the high empty band. The band gathers yep. Sick. Sick. Band below it to jump into the upper empty band by thermal excitation. The solid is known as a semiconductor. Decreases with temperature, the conductivity of semiconductors increases with temperature. The extent can be provided by absorption of light. Most semiconductors are photoconductors. Negative elements are yep. If this new band is situated within a forbidden region, creates a new and smaller band gap with conductivity. Hide the headstock. Huge based on ability to tailor to band gap. If desired application manager provide impurity on the one like the lattice. The dopant elements are normally atoms with values in 1 electron more or less than atomic or crystal. Thermal properties and N-type materials. That's important. This is important with a couple of because I want to show think about uploading high quality videos or uploading videos more consistently and see what comes. Hold on. What do you think about uploading high quality videos or uploading videos more consistently and see what comes? I am kind of stuck between a rock and a hard place at this point because I kind of am trying to do both. And well, is the result, I suppose. The result being I am not uploading consistently and videos aren't that high of quality. But yeah, I'll rather upload higher quality. It's just right now I'm working on 3 videos all at once, so once I actually finished one of them, it's gonna be a lot of uploads. A phosphorus atom there's an impurity is that can cause one valence n-time superconductor. Okay. Chris, what amounts? Yeah, but what is the like practical difference between? P and N-type materials are brought into contact, creating P-N junction. Holes in the P material and electrons in the N material drift towards and neutralize each other, creating a depletion region that is devoid of charge carriers, but the destruction of these carriers leaves more positive ions on the N material, negative ions on the P material, giving rise to an interfacial potential difference depicted here. Okay. Wow. This is once again gonna be so annoying. Hi there, people. This is gonna be so annoying because you have P and N, and so the positive side has great. Positive ions are gonna be in the negative material and negative ions in the positive. Okay. Simple. It's simple to remember, right? So P will stand for negative and N will stand for positive. In this case. It acts to resist the further diffusion into holes, carry free depleted region, which acts as a barrier at the junction. Yeah, so this will be the barrier. Okay, so okay. So the P would be in the junction. P is negative and it's positive. If I'm understanding this correctly, if you bring positive charge to the negative P, then this will destroy the barrier and then the current will flow. The truth is that I think the same. I'm really glad because then high collectivities will come. Okay. I think P-N junction part 1. This is about a bit of a different topic than we're doing, so we are now ready to make an actual useful device. Let's take a piece of N-type material and a piece of P-type material, stick them together. This way we will be making a P-N junction or a diode, which will be our first electric device other than a simple resistor. This band diagram might be like figure, yes. Okay, this makes sense. This actually makes sense. This actually makes a lot of sense. Okay. It makes sense. Okay. Hear me out. This makes sense. Because you have the P side, which is negative, and an N side, which is positive, and then in between them you have a barrier, and so you need to modify one of these sides in order to kind of demolish the barrier, and then this would allow current to only flow one way. This makes sense. Okay. Oh my goodness, this makes sense. Who knows? We're learning transistors. It can disrupt. Oh no, this is okay. This is great. This makes sense. This makes so much sense. Drawn the constant Fermi level. Fermi energy will be the same between good and changes. Okay. Let's see if I'm correct. There's still problems with one diagram, a bunch of holes and drawing a bunch of holes. That we would expect that in absence of some the hole is an absence of an electron, since the electron the conductor but can lower this energy by forming the one. The energy this will happen. It always go with a combination. It will most likely goes with each other junction. Yeah. Tell me if I'm right. That's all I care about. Are you goober? The only reasonable build in backup battles. Seeing that this recombination effect might just go on and on until there are no crystal assembled. This is not the case, however, in order to see the hunt as picture of preferential, yes. They are stuck in a silicon crystal lattice. In reality, however, even though they are stuck in crystal lattice, just a few of them compared to silicon atoms, their distribution would be quite random. As electrons, we will stay the circuit of charges and them. Make it. What happened? Holes and electrons in injection to combine the one electron and a hole recombine. Hi Jürgen. Hi, welcome. Annihilate and disappear. Yeah, well, that makes perfect sense. Kind of know that this process conserves charge, and if we could calculate it, the momentum as well. There is obviously some energy lost, but this is simply short pressure to heal the crystallography. Yeah. I'll make a sake of an imaginary radius, don't we all? Closely at these pictures, you will notice something. As we remove more and more electrons and holes, we are starting to uncover the fixed charges associated with donors and acceptors. We are making what is known as depletion region, so named because it depletes of mobile carriers, yes. The uncovered net charge depletion region is separated, with negative charge in the P region and positive charge in the N region, because obviously P stands for negative, and positive, and N stands for positive, okay? P stands for negative and N stands for positive. It's simple stuff. What will such a charge separation give rise to? Why, an electric field, of course. Which way will the field point? Only one. That's actually, I'm guessing, okay, before we read further on, I'm guessing the point is that they will point only one way, which means that they won't flow the other way. I'm guessing. This field, the right from separation of charges always goes from the positive charge towards negative charge. Yes. By the way, things go from the positive to negative, because it wasn't confusing enough. It seemed like it works. I won't give you tea in this. Listen, I'm gaming. What affects us this device will eventually push holes back into the P region and electrons into the N region. This is just what we need to contract the combination which has been going on, hopefully bring it to stop precisely only one way. Now try to think of what this field could have an energy band diagram. The band diagram for the electrons of the right, the left side, the region of the left side will have to move to the electric field motion, but the discontinuity moving electron cancel must be continuous across the PN junction, but we can't fix this by making a smoother connection between two bands. The electron has to do some work. In other words, potential energy for the electrons must go up, but there is a shift in potential energy as an electron moves from right to left across the junction. Yes. He's locked in. I'm born to dilly-dally, but forced to lock in. This built-in potential keeps majority of holes in the P region and electrons in the N region. Provides a potential barrier which prevents current flow across the junction. On the band diagram, we have to multiply the built-in material, but built-in potential. That's what material makes sense by a charge of electron Q, so we can represent the shift in energy in terms of electron volts. Not hard to figure out. I don't know if we exactly know for equations, since N is equal to indeed. Sorry about that. And P is equal to NA. In the P region, we can relate the distance of the Fermi level from EC and EF by... I won't even pretend to know what's going on because I skipped a couple chapters. You saw me skip over those chapters. I'm still kind of hoping we can speedrun this a bit and get the transistors in time. And see if you agree that I trust you with my life. You always know that an equation will be fun when there's an actual logarithm in it. ND and NA are doping densities. Oh, I remember those. Those are like impurities, kind of, in the NP region, respectively. Remember that KT is equal to... Wait, so... here the Q in front of V by I, is, and the E in EV are both charge of one electron, and they cancel out, making this. I'm my fifth car ride to San and saw that you were streaming, so I decided to tune in. Only spoken by Tribe in Atlantis. Wait, you are on your fifth car ride to San? Good for you. Nice, brother, don't. Germany is 10 AM. Yeah, it's actually quite an early stream for Europe. From physical science. Oh, hold on. I skip over a couple. Sorry, for that. PNP just the nice. Well, not quite nice yet. We haven't really gotten there. Internship. Good for you. Really good for you. I'm really glad. Internship. That sounds great. Internship is actually constant. The work with no pay. Not all internships are unpaid. Head stack. That's only me. Only I do. only I give people unpaid internships. Internships are mostly about learning. If I'm not mistaken, I don't know. I'm a leech on society. I'm a YouTuber. I've never worked a day in my life. I just. ND and NA are about 10 to 15 non-uncommon values. How big would the building potential be in this case? Okay, so. Name that. I'm still underage, so you can't call that work too much. But still, it's an internship. It's cool. It's really cool. Okay, let's make sense of this equation. So, QV, so Q voltage B. Okay, so Q in front of the E are both charged of one electron, and they cancel out, making. Okay, so hold on. Okay, so this is in electron charge volts as units, if I'm understanding this correctly. And since we have a Q right here, we can just cancel out that unit, which would leave us with voltage is equal to voltage, or in other words, the potential. Which means that the potential... Oh wait, we can't cancel that. Well, technically this would have to be divided by Q, doesn't matter. The point is, so we have the potential, hold on, PI. Good morning. Hi, the Mint. Welcome. VBI. This. Built-in potential, that's what it's called. Alright. So the built-in potential, this right here, is equal to morning. I guess it is morning. It's still confusing. Oh my goodness, this. Oh, nothing like a good PNP transistor stream to to start the day. There are so many energies. There are so many energies. Okay. 4:36 p.m. I should restream it at 4:56 p.m. So, building potential is equal to then. We can write this in the Fermi from level EC and EF. Could I have a quick a reminder of what EF is? No? I guess no need for... Okay, cool. So no, the answer is no. Okay, cool. It's okay. So we have. Oh, but we know what N's are. N is the doping density. Well, DNA is the doping density. What is C and... Was that V or is that B? B would make sense. That's a V. Why is that V? We have A, C, D. We don't have B, but we have V. This is great. What's the website? It's LibraText, and it's really great. It has information about absolutely everything. Would recommend. The sponsor of today's live stream is no one. I really wish they would sponsor me. LibraText. It's great. It's fantastic. It's beloved by me. What is NV? I'm gonna skip over the whole why did they skip B. I'm gonna... What is N? Because N... Yeah, because those are doping densities, makes sense. Which would suggest that NC and NV are doping densities of other places. Right? School on Singapore time. Don't worry, most people are missing 75% of my streams because I just don't have a streaming schedule. I just stream wherever, whenever, and wherever, and however. And what is NV and NC? We need to go back a chapter. I'm guessing NC would probably be... Okay, we need to go back 2 chapters. That's probably explains why I haven't seen it. I'm guessing NC would be like the doping of... No, wait, doping wouldn't make really much sense for the whole circuit, would it? NAND, okay. NC, NV, okay, great. Great. Both NC and NV are constants that depend on the material and temperature you are talking about, but are typically on order... Hold on. Okay, so the answer is somewhere in here. Sick. That's fine. Let's... Let's go. Simple. Simple stuff. Easy stuff. Nice little simple live stream to start today. A semiconductor which is the except the semiconductors don't lend them we can assume that those are fully unless the percent instruction the number of those is much greater than if ND is the density of donors in the material, then N, the electron concentration, is roughly equal to ND. Makes sense. If an electron deficient in material such as boron represented... Wait! Would NC and NV be like the density of... whatever the opposite of donor would be? Then the ratio would make sense. Then the ratio would make a lot of sense. Depending on the material and temperature you are talking about, but are typically of the order 10... 19... centimeters negative third. That's basically the opposite of a volume. This is inverse volume. I've never seen inverse volume. What a wild unit. Okay, the expression in the denominator. I mean, it makes sense, but still comical. The expression in the denominator of the exponential is just Boltzmann constant. K times temperature T of material. Okay, so... Wow, this is fun. I'm having so much fun. Who suggested this, by the way? Who suggested this live stream? I hope you're getting a live stream. Hi, the bomb. Hell no. Alright, it's simple. Product resolution must remain constant. Thus, if we have an nth sample of silicon doped with 10 to 17 donors per cubic centimeter, then N, the initial concentration is 10 to 17th, and P, the whole concentration, is this. All the carriers are called minority carriers. Wait, is it about all the carriers? No, that doesn't make any sense. Hi, the Pizza Ranger. Electricity is a miniature magic man carry energy around the circuit. Spot on. of cups of different amount energies used for connecting protons and they were going to the so awkward when you start looking at the device. Why am I looking through this? By the way, we all get how diet works now. Why am I doing this to myself? This was supposed to be a short live stream about PNP. You know what? We're gonna leave it for a future live stream, all of this, because I will be making a video about this soon. So we're gonna leave it for now. The professional that I am. And we're gonna get to pets. Sick. MOSFETs. Make it. Is the end of the stream a summary of the topic? Not always. Sometimes. Oh, well, yeah, we finally get it. Because N, this is the positive, and this is the negative. When they are... And right here you have like a... Okay, this is so simple now. We all get it, right? This is the positive because it's N, and P stands for negative, right? Simple. And then you have a barrier right here. Easy. Cool. Okay. We have a block of silicon, doped P-type. Within it we have two regions which are doped N-type. To each of those N-type regions we attach a wire and connect the battery between them. If we try to get some current I to flow through the structure, nothing will happen, because the NP junction on the right side is reverse bias. Precisely, you would need this to be P, this to be N in order to actually for it to actually flow through. Sick. The stream will be making mounting someone's name to charity. That is most time it happens. If we try to get some current, yeah, we have the positive battery going to the inside of the pin function. If we attempt to remedy this by turning the battery around, we'll now have the LJ's function reverse bias. Yeah, and again, nothing will flow. If, for whatever reason, we want current to flow, you'll need to come up with a way of forming a layer of N-type material between one N region and the other. This will then connect them together and can run the current in one terminal but not the other. I see. Use AdSense with Doofenshmirtz. I'm not good with voices. Okay, I think I get so far. I won't lie, I don't really care about the actual physics this time. I mostly care about theory. So it's really great I'm reading a textbook about actual physics. I'm so smart. Hi, the Crumbly. I think we could be great different. Thank you. Finally. Someone understanding what I'm all about. Okay. I'm most looking for the theoretical. Well, okay, this is theoretical. I just want to know what a PNP transistor does. That's it. There we go. Yes. This is what I was looking for. This is something we can actually understand. Yeah, okay, I think... Okay, cool. So we have 2N, a P, and this is also an N, right? That's an N, right? I'm correct, right? I'm not... Okay. Making music at static. This is making music. Well, not my music. It's Soda's music. YouTube.com/@SodaKCMusic. Go and listen to all this music, amazing music in the background. And YouTube.com/@SodaKCMusic. First, okay. We're forming a layer of N-type material between one N region and the other. So this is N-type material. Okay. So, if I'm listening this correctly, we have N, which is positive, and thus I have woken 4 hours. I have a problem. Go to sleep now. No more watching live stream. No more drinking or anything. Just now. I will not. Hold on. I need a second to gather my thoughts. Okay. Pizza. Where do you walk? Supermarket. Well, yeah, I suppose. I mean, arriving sleepy ain't bad, but still. Just a quick nap. It's midday and I'm doing math or watching a stream about the topic I have no idea about. Life is good. Mate, don't worry. I'm streaming a live stream about the topic which I have no idea about. Like, have you seen this? This is an N drain, N source, this is an N material, this is P-type substrate. So basically, you have. So the basic idea is that, like, you know, you get it, right? I don't have to explain the thing. It's so simple. You have this, which is positive, this which is negative, this which is positive, this which is positive, and so basically, but like, so this one has holes. So okay, so this one has holes, and these don't. These have the opposite of holes. These have fills. These have fills. This has holes, right? What does the VGS refer to? Don't wait. We're not there yet. Okay, but hold your horses. Which means that. Right here, we have the negative side and the positive. And if I'm not a big stinky dumb idiot, then I think I'll be pretty on some solid grounds to say that this means electrons, this means lack of electrons. And then, so electrons are going this way, but this one is full of but this one is already full of fields, and so basically what's happening is that is that they can't pass through actually, because while right here we have fills and right here we have holes, right here we have holes which are filled in, right? You'll get it, right? Yeah. So here we have holes which are filled in. So fills, holes, filled in holes. And so it can't pass through because the electrons have no holes. They need holes. They don't need fills. Or filled in holes. And so what's happening is that right here you have fills, but then when this current comes around, this is a plus, and plus is the lack of electrons, so these are holes, and so these become from fills, they become filled in holes, and then if you give it even more current, they become holes, And so then this passes through those into the other one, where these holes turn this into holes, and then it passes through. That's how quantum mechanics works. That's how quantum mechanics works, everyone. You have fills, you have holes, and you have fill holes. That's simple. Fill structure, the same material and then parts of hole. No, they have fills. Well, you're not understanding, Bombi. It's all simple. They're fills. They're electron fills. And you have electron holes. And then electron filled holes. So just an electron. It's all clear. Oh, I get it all now. Oh, I get it. Finally, I get it. I feel like I'm having a stroke. Okay. So now that this phenomenal explanation is over, absolutely clear, precisely. So most of you probably already know that I'm working on video about chemistry with an actual chemist, and then a sequel to that video will be electricity or electronics from the perspective of chemistry. This music fits perfectly to make it slowly losing its sanity, thank you. So yeah, right now I'm almost done with the video about chemistry, which I'm making with an actual chemist, and then soon I'll make a sequel to that video about electricity with a chemistry basis, and this textbook will be perfect, absolutely perfect for that video. At this point I think that video will be just this textbook. I'm just gonna start the video by saying this entire video is just based on this textbook, and that's it. The arrow over D refers to what? Bommy, we went over this. Don't. This isn't real. This is not a real art. No, you have to remember that, like, that drawings are a social construct. So, like, you know. I have no idea what you're talking about. Okay, Bommy, listen. It's all simple. Okay. It's simple. See, simple stuff. I know what arrow you're referring to, man. That's crazy. That's crazy. No arrow, no problem. That's a good tip for y'all. If you're solving like a differential equation, you've got a one partial derivative, because, you know, it's just a bit too annoying. Just erase it. No partial derivative, no problem. I really am astonished. This is great. Oh, so now that we are done with this spot-on explanation of how a MOSFET works, because this was MOSFET this entire time, right? So that's great. Now we understand how MOSFETs work, which basically means that the... Hold on, let me actually read this. I'm curious. I add an oxide layer to the gate structure, not the battery. Can invert the region under the gate and connect two and the root together. We also identified some names for the part of the structure, so we'll know what we're talking about. The regions, which will be clear later, we call the N region connected to the negative side of the battery, the source, and the other one the drain. Wait, this actually so far makes sense. We will ground the source and also the P-type substrate. We add two batteries, VGS to the gate, and the source. Gate and source, and drain and source. So just wait, you precisely just erase the whole equation. No equation. It will be helpful if we add. It will be helpful if we also make another sketch which gives us a perspective view of the device. For this, we strip off the gate and oxide, but we will imagine that we have applied a voltage greater than VT to the gate. So there is an N-type region called the channel, which connects it to this. We will assume that the channel region has length L and width W. Oh my god, this is deep, huh? Next, we want to take a look at the little section of the channel and find its resistance dr with little section when the little section is dx long. Different from resistance from a normal We now simply divide both sides by L and we end up with expression for the drain current. There's a drain voltage source, the gate voltage, and now which is equal to resistance most transistor. This is obviously not as bad as it could be. Honestly, this isn't too bad. All this kind of like in comparison to what it could be like, using just using just an integral in the simplest way possible that an integral could be used is pretty light, so that's cool. Thus, voltage so voltage from C goes to S. So this voltage goes from here to here. No. Oh, from here to here, same thing. I think. Net charge and C, okay, just... I give up. This requires its own live stream. I give up. I'm done. I am finished. I'm finished and I need a no. You know what we're gonna do? Next live stream probably won't be about this. We're gonna do a whole separate live stream for the future. Or actually a series of live streams probably. Let's be real. We won't do it in a single live stream. Going throughout this entire book because this book is actually looks really fun. When did I even start? Because we started the 3rd chapter. Finished? Yeah, I'm done. Well, I wouldn't say finished. I would say done with this. BS, I am no more. Please. I like my sanity and no, you're making explain poorly principle. How about you explain yourself when you're doing in this live stream instead of spending some time outside? Y'all are just watching way too much YouTube nowadays. Anyhow. We will need a whole separate series of live streams just about this book. Which is fun. Ethical use of engineering materials. Okay, you piqued my interest. Okay, this is amazing. This is outside. I love this. More. Okay, I have a deal for you. I'll go right now. But I will upload a video in 48 hours. How about that? Is that a deal? Let me take my stopwatch. Is that a deal? I go now, but I upload the video in 48 hours. Okay, alright. I'm starting the timer. There. Consider the timer already going. And in 48 hours there will be video. If not, then I'll... No. We'll think of a punishment if I fail. There. I'm sending it onto the interns chat. Consider the timer timing. Alright then. 47 hours. Or maybe less. Or maybe, well, hopefully not more, right? It's kind of the idea of a timer. Alright, new video in 48 hours then. For now, that'll be it. Thank you everyone so much for watching, and have a great day. Bye.